The Type 59 radar operator adjusted his headset and swept his scope across the night sky north of Hanoi. September 1972. He'd been tracking American aircraft for 3 years now, and the patterns had become predictable. B-52s came in waves, big, lumbering radar signatures you could spot 70 kilometers out. F-4 Phantoms flew escort, their afterburners leaving hot infrared trails his SA-2 missile crews could follow straight to the target. The system worked. They'd shot down over 200 American aircraft using this integrated air defense network the Soviets had installed. His station commander stood behind him, arms crossed, watching the green phosphor display. Anything? Clear skies, Comrade Major. Nothing within range. The commander nodded. Their position controlled the northeastern approach to the capital, the most heavily defended airspace on Earth. 32 separate radar installations networked together, feeding targeting data to 200 surface-to-air missile batteries. Every square meter of sky above 10,000 feet was covered by overlapping radar zones. The Americans called it Ring of Steel. Soviet advisors called it impenetrable. At the SA-2 battery 3 kilometers west, the missile crew ran through evening checks. 6 ready missiles pointed skyward, their 195-kilogram warheads capable of destroying anything within 30 meters of detonation. The battery commander had personally overseen today's radar calibration. His equipment could track a single fighter aircraft at 40 kilometers, could differentiate between an F-4 and an F-105 by radar cross-section alone. Fire control radar operational, his technician reported. All missiles hot. The infrared scanning station reported in next. Their latest Soviet equipment could detect jet exhaust heat from 25 kilometers away. Useful backup when Americans tried flying below radar coverage. The operator watched his display, methodical, thorough. Nothing moved in the thermal spectrum. Underground, in the reinforced command bunker, the defense coordinator studied his master plot. Every radar station, every missile battery, every anti-aircraft gun emplacement showed green. Ready. The Americans would come tonight. They always did during good weather. And his integrated system would see them coming from the moment they crossed into North Vietnamese airspace. He'd briefed his crews that morning. The Americans have technology, yes. Electronic countermeasures, chaff, jamming pods. But radar waves don't lie. Metal reflects electromagnetic energy. Physics doesn't negotiate. You cannot hide a 10-ton aircraft traveling 600 kilometers per hour at 20,000 feet. Impossible. His deputy agreed. They'd studied every American penetration attempt for 4 years. The patterns were clear. High-altitude bombers created massive radar returns. Low-altitude attackers showed up on infrared. The integrated defense network had overlapping redundancies specifically designed to eliminate blind spots. The radar operator took another sweep. Still nothing. He noted the time in his log. 147 hours. Clear skies, no contacts. His commander left to check the other stations. 60 kilometers north, something moved through the darkness. No radar signature. No infrared bloom. No engine noise carrying across the jungle canopy. The Type 59 operator's screen remained empty, showing only the faint ground clutter he'd learned to filter out years ago. At 22:03 hours, the fuel depot at Yen Vien exploded. Then the railway switching station. Then the petroleum storage facility. 3 strategic targets, 3 direct hits, 16 seconds apart. The radar operator stared at his empty screen, hands frozen on the controls. His commander sprinted back into the room, shouting into the radio net. All stations report. Who had the contact? Who tracked them? Station after station reported the same thing. Negative radar contact. No infrared signature. No visual confirmation. The Type 59 operator's hand started shaking. Nothing on his scope. Nothing in the sky. But something had just struck 3 hardened targets with precision ordnance, and his billion-ruble defense network hadn't detected a single aircraft. Physics, he'd been told, doesn't negotiate. The morning damage assessment made it worse. American bombs had penetrated the Yen Vien fuel depot's reinforced concrete roof. precision hits through ventilation shafts that required exact coordinates and clear visual targeting. The switching station's control building had been destroyed by a single weapon that entered through the eastern window. Impossible navigation, impossible accuracy, impossible to accomplish without extended loitering time over the target. Yet 23 separate radar installations had recorded nothing. The defense coordinator stood in the smoking ruins of the fuel depot, Soviet technical manual in hand. He'd cross-referenced every page the night before, checking detection thresholds, radar frequencies, calibration specifications. The Type 59 radars operated at 2.695 to 2.755 gigahertz, frequencies specifically chosen because American aircraft couldn't absorb or deflect them. The wave physics were straightforward. Metal surfaces larger than half the wavelength created detectable reflections. An F-4 Phantom generated a radar cross-section of 5 square meters. A B-52 generated a signature exceeding 20 square meters. His deputy approached with the infrared station report. "Comrade Colonel, they detected nothing. Not even residual heat signatures after the explosions. Check the equipment again. We've checked 3 times. Everything operational." The coordinator walked the perimeter of the destroyed fuel depot. The bomb craters showed impact angles consistent with weapons released from medium altitude, 15 to 20,000 feet based on the forensic analysis. But medium altitude meant extended exposure time. His missiles needed only 45 seconds from launch to intercept at that range. The attacking aircraft would have been vulnerable for at least 2 minutes during their approach and attack run. His radio operator jogged across the rubble. "Colonel, Hanoi sector reports the same phenomenon last night. The radio relay station at Baghdad, destroyed at 2156 hours. No radar contact." "That's 13 minutes before our strikes." "Yes, sir. They're requesting we share any tracking data." The coordinator had no tracking data to share. He had empty radar logs, confused operators, and 3 smoldering craters where strategic infrastructure had stood 8 hours ago. By afternoon, the reports multiplied. The bridge at Thang Hoa, attacked, no radar contact. The ammunition depot at Vinh, direct hit, no infrared signature. The Pattern Recognition Center in Hanoi compiled sighting reports from ground observers. 17 separate witnesses reported hearing explosions, but not one reported seeing aircraft or contrails or anything in the sky. The missile battery commander arrived with his firing solution calculations. "Colonel, I've run the numbers assuming they're using some new jamming technology. Even if they're spoofing our radar with false returns, the infrared stations should detect engine heat. Even if they're flying below our radar coverage, the acoustic sensors should hear them." He spread his charts across the hood of a truck. "I cannot create a firing solution against a target that doesn't exist in any spectrum." A Soviet technical advisor arrived from Hanoi that evening. He carried classified briefing materials and wore the insignia of the GRU, military intelligence. The coordinator met him in the underground command bunker. "Your report mentioned 0 radar cross-section," the Soviet said. "Correct, across all frequencies." "And no infrared signature." "Correct." The Soviet advisor opened his briefcase and removed a physics textbook. "This is impossible. You understand? Not difficult. Impossible. Radar cross-section cannot be eliminated. It can only be reduced through shaping, and even the most optimized shape creates some reflection." He tapped the page. "The Americans don't have this technology. No one does." The coordinator gestured toward the window, toward the smoking ruins visible on the horizon. "Then what attacked us?" The Soviet advisor closed his textbook. He had no answer. Moscow dispatched a full technical investigation team within 48 hours. 6 specialists from the Radio Electronics Institute, 3 radar engineers from the PVO Strany Air Defense Command, and 2 physicists from the Ministry of Defense Research Directorate. They arrived in Hanoi with 8 crates of diagnostic equipment and absolute confidence that the North Vietnamese operators had made calibration errors. The lead investigator, Colonel Dmitry Volkov, set up his analysis station in the main radar facility. He designed components of the SA-2 guidance system himself. 30 years of radar engineering. He knew exactly how electromagnetic radiation behaved. "Run the self-diagnostics," he told the Vietnamese operators. "All stations, full-spectrum sweep." The results came back clean. Every radar installation operated within specifications. Volkov had them test the Type 59 systems against known targets, MiG fighters performing calibration runs at various altitudes. The radar tracked each aircraft perfectly, displaying accurate range, altitude, and velocity data. "Your equipment functions correctly," Volkov admitted, "so we examined the attack profiles." His team reconstructed the September strikes using crater analysis, bomb fragment forensics, and impact timing. The data revealed a troubling pattern. The weapons were standard American Mark 84 2,000-pound bombs, nothing exotic, nothing new. The delivery altitudes ranged from 12 to 18,000 feet based on impact angles. The attack headings came from multiple directions, suggesting either multiple aircraft or a single platform making multiple passes. "Multiple passes," Volkov muttered, staring at his charts. "That means loiter time, slow speed, maximum radar exposure." He turned to his deputy. "What's the minimum time between these impacts?" "Bac Giang and Yen Vien, 17 minutes apart, 112 kilometers distance." Volkov did the calculation. Subsonic speeds, 600, maybe 700 kilometers per hour maximum. He circled the attack coordinates on his map. "Flying slow, medium altitude, straight line approaches. This should be the easiest interception scenario we have." But the theory broke down when confronted with radar logs. 23 installations had recorded nothing, not even anomalies, not momentary contacts or unexplained clutter, just empty air where aircraft should have been. The Soviet physicists proposed alternative explanations. Perhaps the Americans had developed plasma stealth, ionized gas surrounding the aircraft that absorbed radar waves. Volkov's team installed additional ionization detectors. They detected nothing unusual during the next attack wave, which destroyed a petroleum facility near Haiphong. Zero radar contact, zero ionization signature. Theory 2, orbital weapons platforms. Precision bombs dropped from satellites, explaining the lack of aircraft signatures. The mathematicians calculated orbital mechanics. Impossible. Satellites couldn't loiter over targets, couldn't adjust aim mid-flight, couldn't achieve the documented accuracy from orbital altitudes. Theory 3, submarine-launched cruise missiles. The Navy installed additional coastal sensors. They detected no submarine activity, no missile launches, and more importantly, the attack profiles didn't match cruise missile trajectories. The weapons came from altitude, not sea-level approach. By November, Volkov had eliminated every conventional explanation. He sat in the command bunker with 3 notebooks full of crossed-out hypotheses, staring at the one conclusion he couldn't accept. "The radar cross-section approaches 0, he said quietly. "Not reduced, nearly eliminated." His deputy looked up from the latest damage reports. "That's thermodynamically impossible. Metal reflects electromagnetic radiation. You taught me that." "I know what I taught you." Volkov pulled out a fresh sheet of paper and began sketching aircraft profiles. "But what if the metal isn't arranged like conventional aircraft? What if the shape is specifically designed to deflect radar energy away from the receiver? The aerodynamics would be terrible." "Yes." Volkov kept sketching, drawing angular surfaces, faceted panels. "Which means they've solved the aerodynamic instability problem somehow. Computers, maybe. Active flight control." He stopped drawing and looked at his deputy. "This isn't electronic warfare, this is engineering. They've built something we didn't think was possible." 14 years earlier, Clarence Kelly Johnson sat in a CIA conference room in Langley, Virginia, staring at requirements that violated every principle of aircraft design he'd spent 30 years mastering. May 1958. The CIA's Richard Bissell had just asked for an aircraft that Soviet radar couldn't detect. "Impossible isn't in the spec sheet," Bissell said, sliding the classified document across the table. Johnson had built the U-2 spy plane for Bissell 3 years earlier, an aircraft that flew at 70,000 feet above Soviet missiles. It worked until it didn't. Francis Gary Powers had been shot down over Sverdlovsk 2 months ago, proving that altitude alone couldn't guarantee invisibility. The Soviets had built better missiles. The CIA needed a different approach. Johnson returned to Lockheed's Skunk Works facility in Burbank, California, and locked himself in his office with a stack of engineering textbooks and a pot of coffee. His team had mastered speed with the SR-71, which used raw velocity to outrun missiles. But speed created heat, and heat created massive infrared signatures. Speed wasn't invisibility. He needed to understand how radar actually worked. Not just the operational theory, the fundamental physics. He called Ed Lovick, his radar specialist. Ed, explain radar cross-section to me, from first principles. Lovick brought his blackboard. Radar waves hit the aircraft, bounce back to the receiver. The amount of energy that returns determines the cross-section. More reflection equals bigger signature. So reduce reflection. Right. Absorb it or deflect it. Lovick sketched wave patterns. Absorption requires special materials, expensive, heavy, marginally effective. Deflection requires precise shaping. The problem is aircraft have curves, fuselages, wings, cockpit canopies. Curves are terrible for deflection. They scatter energy in all directions, and some always bounces back to the receiver. Johnson stared at the wave diagrams. What if there were no curves? What do you mean? Flat surfaces, angles, facets. Johnson grabbed the chalk and drew a diamond shape. What if the entire aircraft was made of flat panels arranged at precise angles? Energy hits a panel, reflects away at a predictable angle, never back toward the radar. Lovick studied the sketch. That's not an airplane. That's a geometric nightmare. Would it work? Theoretically, maybe. But Kelly, that thing wouldn't fly. Aerodynamic lift requires curved surfaces, airfoil shapes. You can't generate stable lift with flat panels at odd angles. Johnson drew more lines, refining the shape. We'll make it fly with computers. Active stability control. The aircraft naturally wants to tumble. Fine. We'll use flight computers to make 10,000 tiny adjustments per second, keeping it stable. That technology doesn't exist. It will. Johnson labeled his sketch Hopeless Diamond, his engineering team's sardonic nickname for the concept. Get me a mathematician, someone who can calculate exactly how electromagnetic waves interact with angled surfaces. Lockheed hired Bill Schroeder, a brilliant mathematician who'd published papers on electromagnetic scattering. Schroeder spent 6 months developing equations that predicted radar reflection based on surface geometry. His calculations proved Johnson's instinct correct. Faceted surfaces could reduce radar cross-section by orders of magnitude, but only if every angle was precisely calculated. The first scale models went into Lockheed's radar test range in 1959. A wooden mock-up covered in radar-absorbent material, mounted on a pole, bombarded with electromagnetic radiation. Schroeder's equations predicted a 90% reduction in radar signature compared to conventional aircraft. The actual measurement showed 95% reduction. Johnson stood in the test range, holding the measurement printout. His hands trembled slightly. He was 50 years old, had designed 14 aircraft, and he'd just proven that radar invisibility wasn't impossible. It was engineering. He walked back to his office and called Bissell. "We can do it, but it won't look like anything you've seen before. It'll handle like a brick, and it'll take 10 years to make operational." Bissell's response was immediate. "Get started." Johnson assembled his team in the Skunk Works secure hangar and unveiled the Hopeless Diamond mock-up. His lead aerodynamicist, Dick Cantrell, circled it twice without speaking. "Kelly, this has the aerodynamic efficiency of a falling anvil." "I know. The radar cross-section reduction is remarkable, but we can't build a reconnaissance aircraft that can't maneuver, can't maintain stable flight, and needs a runway the length of California to land." Johnson pointed to the faceted surfaces. Every panel is angled to deflect radar energy. Bill's equations prove it works. We measured it, 95% reduction. The Soviets won't see this coming until it's directly overhead. If it can get overhead, Kelly, the lift-to-drag ratio is terrible. The center of pressure shifts constantly depending on angle of attack. 1 degree off optimal and it departs controlled flight. So we don't let it get 1 degree off. Johnson spread his flight control diagrams across the workbench. Honeywell is developing digital flight control computers for the lunar module. We adapt that technology. 3 redundant computers making constant adjustments. The pilot gives commands, climb, turn, descend, and the computer figures out which control surfaces to move and by how much. Cantrell studied the control system schematics. You're asking the computer to do what human reflexes can't, maintain stability in an inherently unstable airframe. Exactly. Human reaction time is 200 milliseconds. The computer reacts in 10 milliseconds, 20 times faster. Johnson pulled out wind tunnel data. We've run 4,000 hours of testing. The shape works if, and only if, the flight control system never fails. And if it does fail, the aircraft tumbles and the pilot ejects, which is why we're building 2 redundant systems with automatic switchover. Bill Schroeder joined them with updated calculations. His radar cross-section equations had become more sophisticated, accounting for different radar frequencies, polarization angles, and aspect ratios. Kelly, I've refined the surface angles. We can reduce the signature another 30% by adjusting the fuselage facets by 2.3 degrees. Johnson examined the numbers. That changes the aerodynamics. It destroys the aerodynamics, Cantrell interjected. We're already at the edge of controllability. Schroeder laid out his electromagnetic scattering plots. But it makes the aircraft nearly invisible to S-band radar, the primary Soviet early warning frequency. At certain aspects, the radar return is less than a square meter. That's smaller than a bird. Johnson made the decision that defined his career. We optimize for stealth. Fix the aerodynamics with computers and pilot skill. The engineering team spent 18 months translating theory into hardware. The airframe required exotic materials, aluminum honeycomb core with composite facings, precisely machined to maintain exact angles. A single panel out of tolerance by 2 millimeters could create a radar hotspot that compromised the entire aircraft. The radar-absorbent coating proved equally challenging. Iron ball paint, microscopic iron spheres suspended in polyurethane, absorbed certain radar frequencies but added weight and required constant maintenance. Ed Lovick's team tested 67 different formulations before finding one that balanced absorption, weight, and durability. In 1977, the first prototype emerged from the hangar. Lockheed designated it Have Blue, an innocuous name that revealed nothing about its revolutionary design. The aircraft looked alien. Faceted surfaces met at hard angles. No curves anywhere. The cockpit canopy was flat, angled precisely to deflect radar. Even the engine inlets were covered by metal grids designed to hide the turbine blades from radar waves. Test pilot Bill Park strapped in for the first flight at Groom Lake, Nevada. The remote base, Area 51 in classified documents, provided isolation from Soviet satellites and curious observers. Johnson watched from the control tower as Park lit the engines. The aircraft rolled down the runway, its angular shape breaking every aesthetic rule of aircraft design. It lifted off. The flight computers kept it stable. Park climbed to 10,000 feet, flew a 15-minute test profile, and landed successfully. Johnson permitted himself a slight smile. Physics hadn't negotiated. Engineering had. The Have Blue prototype proved the concept. Now Johnson's team faced the harder problem, turning a fragile demonstrator into an operational weapon. The Air Force wanted a strike aircraft, not a reconnaissance platform. Something that could penetrate Soviet air defenses, destroy high-value targets, and return to base. Lockheed designated the production version F-117 Nighthawk. The name was deliberate misdirection, the F fighter designation instead of A for attack. designed to confuse Soviet intelligence analysts who might intercept communications about the program. The engineering challenges multiplied with operational requirements. The Have Blue carried no weapons. The F-117 needed an internal weapons bay large enough for two 2,000-pound laser-guided bombs while maintaining radar signature discipline. Opening the bay doors during weapons release created temporary radar spikes, brief moments of visibility that Soviet operators might detect. Alan Brown, the weapons integration lead, solved it with geometry. The bay doors are faceted like the rest of the aircraft. When they open, they create angled surfaces that still deflect most radar energy. We limit door open time to 15 seconds, just long enough to release weapons and close back up. The production aircraft grew larger than Have Blue, 62 feet long, 43-foot wingspan. Heavier, too, at 5,500 pounds maximum takeoff weight. Two General Electric F-404 engines buried deep in the fuselage, their infrared signatures masked by clever exhaust mixing that cooled the turbine gases before they exited through slots instead of conventional nozzles. Test pilot Hal Farley flew the first F-117 production aircraft in June 1981. His classified flight report contained one line that justified 5 years of engineering. Radar test range confirms cross-section less than 0.01 square meters at optimal aspect, equivalent to a hummingbird. The Air Force built 59 F-117s in complete secrecy. Each aircraft cost $43 million, expensive, but cheaper than losing conventional bombers to Soviet SAMs. The manufacturing facility at Burbank operated under cover stories. Workers told families they built aircraft components. Security clearances went 4 levels deep. No one outside the program knew what the angular black aircraft actually did. Pilot training happened entirely at night at Tonopah Test Range in Nevada. The 4450th Tactical Group's pilots learned to fly an aircraft that handled nothing like conventional fighters. The faceted surfaces created unpredictable airflow. The flight computers compensated for instability, but pilots still needed to adapt their technique. Major Alton Whitley, one of the first operational pilots, described the learning curve. You don't fly the F-117. You tell it where you want to go and trust the computers to get you there. Try to muscle it like an F-4 and you'll depart controlled flight immediately. It demands smooth inputs, patience, and absolute faith in the automation. The aircraft had limitations, subsonic only. Speed created radar signatures. No air-to-air capability. The stealth shaping couldn't accommodate external weapons. No radar of its own, emitting electromagnetic radiation would announce the aircraft's presence. Pilots navigated using infrared targeting systems and pre-programmed coordinates loaded before takeoff. But within those constraints, the F-117 could do what no other aircraft could. Fly through defended airspace as if the defenses didn't exist. Soviet radar operators would see nothing. Infrared sensors would detect nothing. Acoustic sensors might hear a faint whisper of turbofans, but by then the bombs were already falling. Johnson retired from Lockheed in 1975 before the F-117 flew, but he'd set the engineering foundation. His obsessive focus on radar cross-section reduction, his willingness to sacrifice conventional aerodynamics for stealth, his insistence on precise manufacturing, all of it crystallized in 59 black aircraft that rewrote the rules of air combat. The Soviet Union, despite Colonel Volkov's increasingly sophisticated theories, never detected the program. They knew something was hitting targets in various theaters. They couldn't prove what. American stealth technology remained the most successful military secret of the Cold War's final decade, until someone finally used it in combat and removed all doubt. The Pentagon's interest in operational stealth aircraft crystallized on April 24, 1980, in the Iranian desert. Operation Eagle Claw, the mission to rescue American hostages from Tehran, collapsed when a helicopter and a C-130 collided during the extraction phase. 8 servicemen died in the fire. The remaining aircraft abandoned the mission and retreated. President Carter's military advisors conducted the post-mortem in the White House Situation Room. The fundamental problem was clear. Conventional aircraft couldn't penetrate defended airspace without massive support packages. The Eagle Claw mission had required 8 helicopters, 6 C-130 transports, and elaborate diversionary tactics. All that complexity, all that coordination, and they'd never even reached Tehran. Colonel James Allen, assigned to the Tactical Requirements Division, wrote a classified assessment that landed on every senior officer's desk. We need an aircraft that requires no support package, no diversionary raids, no elaborate coordination. Something that can fly alone, strike precisely, and exit before anyone knows it was there. The F-117 program, still highly classified, represented exactly that capability. Allen's report accelerated the operational timeline. The Air Force activated the 4450th Tactical Group at Tonopah in October 1981 with a specific mission profile: surgical strikes against time-sensitive, heavily defended targets. The pilots trained for scenarios that conventional aircraft couldn't attempt. Single-ship penetration missions, no electronic warfare support, no fighter escort, no jamming aircraft. Just one F-117, one pilot, 2 bombs, and preloaded target coordinates. Major Jerry Leatherman flew some of the early training missions. They'd give us a scenario: chemical weapons facility in hostile territory, defended by Soviet-patterned SAM systems. Our job was to fly through the defenses, destroy the primary target building, and egress without being detected. The mission planning was surgical. We'd study satellite imagery for hours, identifying the exact aim point, calculating wind drift, planning the approach to minimize exposure time, even though radar couldn't see us anyway. The training scenarios grew more ambitious: multiple targets in a single mission, attacks through weather, precision strikes requiring weapons placement within 3 meters of the designated impact point. The laser-guided bombs could achieve that accuracy, but only if the pilot maintained steady flight during the terminal guidance phase. No evasive maneuvers, no defensive reactions, just straight and level flight while riding an invisible aircraft through enemy airspace. Psychological training proved as important as technical skills. Conventional pilots relied on situational awareness, radio calls from AWACS controllers, missile launch warnings, threat indicators. F-117 pilots flew in radio silence through defended airspace with no external information. They trusted the stealth technology absolutely. One pilot described it as faith-based flying. You believe the physics, or you don't belong in the cockpit. The 4450th practiced the entire kill chain. Mission planning teams developed target folders. Intelligence analysts identified high-value targets. Weapons specialists selected appropriate munitions. Pilots flew the profiles at night, simulating combat conditions. Maintenance crews kept the aircraft's stealth coating pristine. Any damage or contamination could create radar hotspots. By 1983, the squadron was operationally ready. The aircraft worked. The pilots were trained. The support infrastructure existed. But the F-117 remained classified. Using it in combat would reveal its existence, potentially compromising the technological advantage. The Pentagon established strict employment criteria. F-117s would only be used when conventional aircraft couldn't accomplish the mission, when the target value justified revealing the capability, or when national security demanded absolute mission success. For 8 years, the 4450th Tactical Group flew training missions in Nevada, waiting for a target that met those criteria. The pilots maintained proficiency. The aircraft remained ready. And somewhere in classified Pentagon files, analysts continued studying historical bombing campaigns, looking for lessons about how invisible aircraft might have changed outcomes. One particular case study kept appearing in their assessments. Linebacker 2, December 1972, North Vietnam. The Pentagon's Historical Analysis Division opened the Linebacker 2 case files in 1985. 13 years after B-52s had hammered North Vietnamese targets during Nixon's Christmas bombing campaign. The official after-action reports documented 729 sorties, 15 B-52s lost, and strategic targets destroyed across the Hanoi-Haiphong corridor. Standard analysis. expected attrition rates against sophisticated air defenses. But buried in the classified annexes, intelligence analysts found something else entirely. Lieutenant Colonel Patricia Harding led the stealth employment study. Her team had been tasked with identifying historical scenarios where low observable aircraft might have provided decisive advantages. She pulled restricted files from the Defense Intelligence Agency archives, North Vietnamese defense communications intercepts, Soviet technical assessments, and debriefings from returning American POWs. One pattern emerged repeatedly. During the final weeks of 1972, North Vietnamese air defense coordination centers reported anomalous bombing incidents. Targets struck with precision. No radar contact. No aircraft observed. The reports had been dismissed at the time as sensor failures or operator errors. Harding cross-referenced those incidents with American operational records. She found something that made her request additional classified material. A small experimental unit operating out of Thailand in late 1972, flying modified A-7 Corsair IIs equipped with radar-absorbent materials and reduced cross-section modifications. The project, codenamed Compass Ghost, had been a proof of concept for reduced radar signature technology. Not true stealth, the modifications only reduced radar cross-section by 30 to 40%, but enough to confuse North Vietnamese operators under specific conditions. Harding obtained the Compass Ghost mission logs. Between November and December 1972, these modified A-7s flew 47 sorties against defended targets in North Vietnam. The missions were deliberately scheduled to test which approach profiles, altitudes, and attack geometries created the most confusion in enemy air defense networks. The data was revelatory. When the modified A-7s attacked from medium altitude at night, North Vietnamese radar operators often failed to acquire tracking solutions. The aircraft's reduced signature fell below the threshold that triggered automatic threat warnings. By the time operators manually detected them, the aircraft had already released weapons and begun egress. More importantly, the psychological effect was profound. A classified CIA report from 1973, obtained from a defecting North Vietnamese intelligence officer, described the impact. Defense crews experienced severe morale degradation when unable to detect attacking aircraft. Training emphasized that proper radar operation guaranteed detection. When detection failed despite proper operation, crews began to doubt their equipment, their training, and their ability to defend critical targets. Harding's team reconstructed the tactical picture. The Compass Ghost tests had been limited. Only partial signature reduction, only certain attack profiles, only a handful of sorties. But they demonstrated a fundamental principle. Reducing detectability created cascading effects beyond simple penetration success. It disrupted defensive coordination, degraded operator confidence, and forced defenders to question their entire tactical doctrine. Her classified report concluded with a straightforward assessment. If 40% radar cross-section reduction produced measurable defensive disruption in 1972, an aircraft with 99% reduction, such as F-117, would render conventional air defenses effectively useless. North Vietnamese operators in 1972 encountered the leading edge of stealth technology. They couldn't explain what they experienced because they lacked the conceptual framework to understand it. The report landed on the desk of Air Force Chief of Staff General Larry Welch. He read it twice, then requested a briefing from the F-117 program office. The North Vietnamese in 1972 were terrified of aircraft they could barely detect, Welch said during the briefing. What happens when we show up with aircraft they can't detect at all? The answer would come 9 years later in the skies over Baghdad. But the North Vietnamese defenders had been the unintentional test subjects, their terror documented in intercepted communications and intelligence reports. Proof that stealth technology didn't just evade radar. It shattered the psychological foundation of air defense itself. January 17, 1991. Baghdad's integrated air defense system was the most sophisticated outside the Soviet Union. French-built carry network connecting over 7,000 radar installations, command centers processing data from overlapping surveillance zones, and 3,000 anti-aircraft guns backed by 16,000 surface-to-air missiles. Iraqi commanders had studied the Vietnam War extensively. They'd learned from North Vietnamese mistakes. Their operators trained constantly. Their equipment was modern, well-maintained, calibrated to NATO standards. At 0238 hours, 10 F-117 Nighthawks crossed into Iraqi airspace. No jamming support, no fighter escort, no diversionary attacks, just 10 angular black aircraft carrying precision-guided weapons toward the most heavily defended targets in Iraq. Communication centers, air defense headquarters, command bunkers. Iraqi radar operators watched their screens show empty sky. The Qari network processed data from multiple installations, finding nothing. Missile battery commanders scanned infrared frequencies, detecting no heat signatures. The integrated system that had cost billions to build and years to perfect reported a completely clear threat picture. At 0251 hours, the telecommunications center in Baghdad exploded. Then the Air Defense Operations Center. Then 3 command bunkers. 8 minutes, 10 targets, 10 direct hits. Iraqi air defense crews scrambled to launch missiles at targets they couldn't detect, couldn't track, couldn't engage. Captain Marcel Kurdavad, flying F-117 Dummer 816, later described the mission. Their radar was active. We could see the emissions on our threat displays. Their missiles were ready, but they were scanning empty air. I flew directly over 3 different SAM sites during my attack run. None of them launched, not because they chose not to. They literally couldn't see me. The psychological impact was immediate and devastating. Iraqi operators had trained for American jamming tactics, for electronic warfare, for saturation attacks. They hadn't trained for invisibility. Within 72 hours, Iraqi air defense crews began abandoning their posts. Not from cowardice, from futility. Their equipment functioned perfectly, but detected nothing while their targets exploded around them. Kelly Johnson had died in 1990, 1 year before the Gulf War, but his obsessive pursuit of radar invisibility, begun in that CIA conference room in 1958, had just validated itself in the most comprehensive way possible. Over 43 nights of combat, F-117s flew 1,271 sorties against heavily defended targets. Not one aircraft was damaged. Not one pilot was lost. The stealth technology that Lockheed engineers had wrestled into existence over 3 decades had performed flawlessly. The North Vietnamese defenders in 1972 had encountered the prototype concept: reduced signatures, confused radar, unexplained strikes. They'd reported their terror to Soviet advisors who couldn't explain what was happening. Colonel Volkov's team had come tantalizingly close to the truth with their sketches of faceted aircraft, but they dismissed it as implausible. The Iraqi defenders in 1991 encountered the matured technology. No ambiguity, no sensor malfunctions, just the absolute proof that conventional air defenses had become obsolete against aircraft designed from first principles to be invisible. The paradigm shift was complete. Every air defense system worldwide now operated under the assumption that attackers might be invisible to radar. Nations scrambled to develop counter-stealth technologies, but the physics remained unchanged. Electromagnetic waves behaved predictably, and Kelly Johnson's team had mastered the geometry of deflection. The terror that North Vietnamese radar operators felt in 1972, staring at empty screens while targets exploded, had become the defining reality of modern air warfare. Not through magic, not through science fiction, through relentless engineering, precise mathematics, and the willingness of one stubborn aircraft designer to pursue an impossible requirement until it became operational reality. Physics, as it turned out, could be negotiated. You just needed the right equations and 30 years of obsessive work.